Hi, something you might have already heard about is the term neural network. In this unit, we are going to take a closer look at what neural networks are, how they function, and what makes them so popular. Neural networks are used for a variety of tasks such as image recognition, recreating a specific art style, or doing machine translation. The term neural network describes a bunch of different but related methods that take input data to deliver useful outputs. Neural networks are loosely inspired by our brain. Our brain is made up of neurons, and a neuron is just a simple unit that takes an incoming signal and, under certain condition, for example when a certain threshold is met, outputs a signal to other neurons. While a single neuron is not very powerful, millions or billions of them are. Their reaction to incoming signals is different for each of those neurons, and this reaction can change or adapt over time, which is an integral part for remembering and learning stuff. We can now use this idea to create an artificial neuron. As you know, computers work with numbers, so the signal this time is an electric signal representing a number. These inputs are then multiplied with weight. Some constant factor called the bias is added, and all the values are summed up. Before the signal is finally outputted, an activation function is applied. More on that in a minute. So essentially, a neuron consists of weighted input, some math, and output. Let's use this sample artificial neuron and input some data. For this, we just added a couple of inputs, weights and a bias. Our artificial neuron takes the input, multiplies it with weight, adds a bias and sums it up. So in this case we have 1 times 0.2 plus 0 times 0.7 and so on. Before we pass on the output, we apply an activation function. Activation function gives the neural networks more options to model the relationship between input and output. Common activation functions used include the rectifier that just takes positive values and replaces every negative value with 0. Using this activation function, the neuron will now output 0.6 as 0.6 positive. Besides the one we used, there are also other activation functions, like one that is called sigmoid that turns negative output into nearly 0 and positive output into nearly 1, with a smooth transition around 0. Just like our brain, a single neuron won't get us anywhere. So we combine our neurons to artificial networks. What we get is an artificial neural network, often pictured like this. We'll now explore what all those nodes and edges, the different layers, and their interconnectedness mean. For this, we need a simple example. Remember the problem from our supervised learning video, where we wanted to classify whether something is a fruit or vegetable, based on the protein and fiber per 100 gram? Let's now see how we can do this with a neural network. Our network is made up of an input layer that takes two inputs, the amount of fiber and the amount of protein per 100 gram, and an output layer. The neuron of the output layer tells us the probability of the input being a vegetable or the probability of the input being a fruit. The input layer receives the input, the output layer predicts the output. But we can also add some layers in between, which we call hidden layers. Input and output layer are still connected, but the hidden layer allows us to cover more complex relationships. The neurons behave like the single neuron we looked at before, with one exception. The output of one layer's neuron serves as an input to each neuron on the next layer. Of course, this is true for every neuron in every layer. Let's now feed an apple with 0.3 grams of protein and 2.4 grams of fiber into our network. The input is given to each neuron of the next layer, the hidden layer. For each of these neurons, we need to calculate the weighted sum of the inputs. So for the first neuron in the hidden layer, that is 0.3 times protein plus 0.7 times fiber, then we add the bias of 0.3 and apply our activation function, which I'll just call AF for short. The same applies to the other neurons in the hidden layer. Instead of using specific numbers, I'll just stick to placeholders here, so W1, W2, and so on. So the second hidden neuron calculates weights W3 times protein plus weight W4 times fiber as the bias applies the activation function, and so on. For the output layer, the same applies. What we computed as the output for the neurons in the hidden layer is now the input for the neurons in the output layer. So we can compute the results for being a vegetable and for being a fruit by calculating the weighted sum of the output of the hidden layer, adding the biases of the output layer, and applying the activation function. Let's imagine we have the following weights and biases in our network. Using those values, we can calculate the output of our network. Like in this case, the network predicts it's a fruit. Essential for predicting the right output is that we use fitting weights and biases. But how do we know what good weights and biases are, and where do these values come from? Until now, we've always assumed that we have a trained neural network in front of us. So let's put our model back in a state before it has been trained. As we only have two input dimensions, we can visualize the decision of our neural network in a 2D plot. In this visualization, we've highlighted the areas where the probability for fruit is higher than for vegetable in red, and where the probability for being a vegetable is higher than for being a fruit in green. So all those points in the green area here are classified as vegetables. As you see, the apple is now classified as a vegetable. This is not quite what we've wanted, but by tweaking the weights and biases, we can adjust the boundary where something is classified as a vegetable or a fruit. As an activation function, I'll just use a simple function for now. This function returns the same value that was used as its argument. I'll start by tweaking the weights now. We have 12 weights in total, so if I change the value of the weights here, we see how the boundary separating the two areas shifts. But unfortunately, just adjusting the weight only allows us to change the slope of the boundary. That's why we also need biases. By adjusting the bias, we can change the x and y intercept of our boundary, but it still only allows us to draw a straight line, which is obviously not enough to fit this data. The solution is to switch to a nonlinear activation function, such as sigmoid. Together with the sigmoid function as an activation function, we now have enough control to separate fruits from vegetables. With this all set, I'll now try to find appropriate weights and biases. So with this we had a lot of trial and error to find the fitting weights and biases, but there must be a better way to do this. And there is. Having the weights and biases determined automatically is the whole point of having neural networks. In this automatic process, called training, the network learns appropriate weights and biases. With this untrained network here, we see the output predicted is not quite what we've wanted. The value for the probability of our apple being a vegetable is 0.56, while the probability for fruit is only 0.42. We'll now use supervised learning to improve the network's prediction. Remember, with supervised learning along with the input, we also provided the expected output. By comparing the predicted and the actual output, we can calculate how big the error is, and based on that error, we now know in which direction and to what amount the parameters need to be adjusted. This information is then transferred backwards through the network so that the weights and biases of each layer can be adapted to minimize the error. A process also known as backpropagation. This process of forwarding inputs through the network and use the predicted and expected output to backpropagate the error is then repeated until our network can predict the correct label in most cases. And the same idea bigger neural networks are based on. The second network we look at recognizes if a hand-drawn digit is a 1, a 2, a 3, a 0, and so on. This is a very famous example for image recognition. Each image is made up of 28 by 28 pixels, and each pixel represents a number between 0 and 1, indicating how light the pixel is. 20 by 28 pixels lead to 784 pixels with a value between 0 and 1 in total, which can be fed as inputs to our neural network. So for each pixel value we feed into our network, we have one input neuron. As we have 784 individual pixels in our network, in our image, our input layer in this case is also made up of 784 individual input neurons. Too much to plot them in two directions. The number of output neurons equals the number of possible categories we want to differentiate. In this case 10, or the digits from 0 to 9. This time we have two hidden layers in between. The hidden layers contain 12 and 8 nodes respectively. This is just an arbitrary choice. Actually tweaking and changing this number can help get better networks. even the number of hidden layers, in this case 2, was just taken for illustration purposes. With a lot of hidden layers, networks can become pretty deep. That's why we sometimes speak of deep learning. Again, the output of one layer's neuron serves as the input to each neuron on the next layer. If we do all the wiring, we end up with a lot of connections. Let's illustrate all outputs with a color. Black means we have a low activation or a value of 0, white means we have a high activation or a value of 1. Gray values are in the middle, depending on how light they are. Doing the simple math for each neuron in the hidden layer, we get outputs on our hidden layer, which serve as input for the next hidden layer, which eventually end up as the output of our neural network in general. In the output layer, you see the activation for the certain third neuron counting from the top is the highest. So, in this case, the network predicts it's easy too. It's easy to grasp what the input layers are, since we have direct links what those values mean. They are pixels. We also know what the outputs mean as we interpret that value, but it's a lot harder to grasp what the values in the hidden layers are representing. Essentially, one node or one neuron on the hidden layer also represents a feature that is made up of features from the layer before, in this case of the first hidden layer. It is some combination of the features representing individual pixels. Looking at the weights of a neuron's inputs helps us to identify how much each feature, or in this case each individual pixel, is taken into account. Even this network, that just takes 28 by 28 pixels, already has around 10,000 weights and biases we can tweak. We might think of this as a giant sound mixer board, where we have to find a perfect combination how to turn all those knobs. Often, neural networks have even more parameters to tweak. That's why sometimes you hear experts saying that they cannot properly explain why specific decisions have been taken by the system. And depending on the size of the neural network and the hardware used, training can take hours, days, or even months to complete. In reality, there are many different types of neural networks that perform well on different types of problems of data. We'll just highlight a couple of them. Both networks we are investigated so far are called feed-forward networks. They feed information forward to predict output, and they're usually trained using supervised learning, giving them a combination of input and expected output so they can backpropagate the error. Assuming we have enough neurons in a hidden layer, such a network, in theory, is able to model every relationship between input and output, regardless of the complexity. In practice, however, there are other hurdles, such as the need for even more weights or even more training data. That's why we have some specific types of network. A type of network specialized on images are convolutional neural networks, or CNNs in short. CNNs use additional types of layers, namely convolutional and pooling layers, to boost performance on tasks such as image recognition. Convolutional layers apply filters on the image, similar to what we do when we use a filter in a photo editing program, for example one that helps us to detect vertical lines. They take a window of pixels, not the whole image, to calculate the value of a new pixel. Using training data, the network can determine which filters should be used. Besides these convolutional layers, CNNs are also featuring pooling layers, where we take, say, 2 by 2 pixels and pass on the pixel with the most amount of red. This reduces the overall number of pixels we need to look at in the next layer. After applying convolutional and pooling layers, CNNs often glue a feed-forward net to the end to further process the data and, for example, decide whether an image contains a cat or a dog. Some neural networks can actually also be trained to generate data, such as deepfakes. The term deepfake describes media that has been generated or changed by AI. Some examples are presented on the website called "This person does not exist." So, she does not exist, she does not exist, he does not exist. Would you've been able to tell? The system uses a so-called generative adversarial network, or GAN. A GAN contains two networks working together. This might be any two types of networks, although often a combination of feed-forward and convolutional neural networks are used. The first network is asked to generate content like the picture of persons from prior input, which can be something scrabbled by the user or just random noise. The second network has to judge the content created. It judges by either saying this data is real or this data is fake, which means it has been generated by the first network. So this starts a form of competition. By applying the same training strategy as before, the second network is getting better at distinguishing real from fake data, and the generator is learning to become better at faking. There are many other types of neural networks, but in general, neural networks support us in dealing with huge amounts of data that we often have with machine learning. At their core, they find a way to transform input values into outputs, the pixels of an image into a caption, a German sentence into an English one, and so on. There is no magic involved, just a lot of clever math. With neural networks becoming increasingly big, it's sometimes really hard to tell why they lead to specific outputs. With all the different weights and biases, we have a really hard time telling which aspects of the input are responsible for which aspects of the output. This was it for today's episode. Thank you guys for watching, and see you tomorrow when we speak about AI in society.